Well, here we are at the last little bit of lecture 4, and here we're going to talk about acid-base titrations. Basically, the controlling of acid-base reaction through stepwise additions. So that's really what titration is. It's the practice of determining the concentration of a substance by reacting it with another. I should probably be more specific, in a controlled manner. Very common method used with acids and bases, but you don't have to do only acid and bases in the titration. There are redox titrations, there are complexation titrations, several different types of titrations that you can do. We're going to focus just on the acid-base titrations. Just be aware that there's other kinds. Now, in our acid-base titrations, we have something that is called an equivalence point. And at that equivalence point, the moles of H plus that have been added are equal to the moles of OH minus that have been added, and they all neutralize each other. So at that point, the acid and the base have neutralized. So the main part of the acid, the main part of the base are gone. And then depending on what you have left determines the pH of where we're at the equivalence point. There is a very common misconception about the equivalence point, and that is that the pH is always at 7, and that is just simply not true. The only time that you are going to have a pH endpoint that's 7 is when you have a strong acid being titrated with a strong base. If you have a weak acid with a strong base or a weak base with a strong acid, your pH is either going to be acidic or basic, and we'll talk a little bit about that as we go along. But we have to get rid of our misconception that the pH at endpoint is always at 7. So here's an example of a strong base titrating a weak acid. So here we are titrating acetic acid here with sodium hydroxide, a strong base. And we've got some interesting regions in here. So when the reaction first starts, notice that it's kind of curved here, rising fairly quickly, and then it begins to taper off as we add a little bit more, base there. We enter something that is called a buffer region here. And the reason this is called a buffer region is because what's happened is you still have some acetic acid present in your solution, because that's what you started with. And then as you add hydroxide, you begin to make some acetate ion. You actually create a buffer solution present in your titration vessel, and since you have a buffer solution, the pH change begins to lessen. You can see that by comparing the slopes. Notice the slope right here is much greater than the slope right here, and that slope represents the change in pH. Notice also right here where the equivalence is, that is not at 7, that is right around 9. It's about 8.7. For the pH at the equivalence point. Now, why is that? Well, if we think about what we have, oops, let's get something to write with. Change color here. We've got our acetic acid. It's going to react with the hydroxide of sodium hydroxide. The H and the OH are going to react and give us water, and what you're left with is some acetate ion. Well, we know that acetate ion is the conjugate base of the weak acid, acetic acid. And because it's the conjugate base of a weak acid, that means that it itself is a weak base and has basic properties. And so that's why we have a basic pH, a pH greater than 7 at equivalence point. It's because even though the original acid and the added base are gone, we've created a new weak base in the process. And at the equivalence point, the only thing left there with acid-base properties is that conjugate base of acetic acid, the acetate ion, and it will give the solution a basic pH. So here it is kind of typed out here. So at the equivalence of a titration, the only things you have left is water and a salt. Now, in that strong acid, strong base titration, the salt that is left are the conjugates of strong acids and strong bases. And as we know, the conjugates of strong acids and strong bases have no acid-base properties. And so the salt that's formed in that type of titration also has no acid-base properties, and so the solution there is neutral. You have formed water and a neutral salt, and so your pH there will be 7. However, as we saw with a weak acid being titrated with a strong base, then the salt that gets left over, in the previous example, that would have been sodium acetate. The acetate is the conjugate base of the weak acid, and so as a result, the equivalence will occur at a basic pH. And there's the example that I just showed you there. Now, if we titrate a weak base with a strong acid, then the only thing that we have left in our salt is a conjugate acid. It'll be the cation of the strong acid combined with the conjugate acid of the weak base, and we're going to have then an acidic salt, and so the equivalence point will occur at an acidic pH. So it depends on the situation that you have. Strong base, strong acid gives us pH of 7. Weak acid, strong base will be basic. Weak base, strong acid, it will be acidic. And there's an example of a weak base being titrated with a strong acid. Now, one of the more common misconceptions I've run into before is that people say, well, the equivalence point for something like a weak acid and strong base is basic because we are adding a strong base. And that simply isn't true. The strong base is gone. It's no longer in solution. That might be a way to remember it, but that is not the reason why that solution is going to be basic. Same with strong acid. People would say that it's acidic because we are adding a strong acid, and that's not true. Okay, at the equivalence point, that strong acid is gone. It's completely neutralized. What causes those solutions to be basic here and acidic here is the acid-base properties of the conjugate of the weak acid or base. So let's look at these in a little bit of detail. Strong acid, strong base. 100% reaction upon addition when they react together. We don't need to worry about any kind of equilibrium because they go just fully towards the products, a single arrow. We can work these problems from the standpoint of moles as far as how much did we add, how many moles did we start with of acid or base, how many moles did we add of acid or base, how much is left over. We can then recalculate concentrations with our new volume based on what we started with and what we added, and from there we can calculate a new pH. Now, when you track the pH of a strong acid, strong base reaction, the pH rises fairly slowly until you begin to near the equivalence point. As soon as you get near the equivalence point, the pH rises extremely rapidly and moves up into either up into the basic or down into the acidic, depending on what you're adding to what. But at that equivalence point, moles of acid are equal to moles of base, and your pH will be equal to 7. And here's an example. If we want to know how many milliliters of 0.61 molar NaOH are needed to neutralize 20 milliliters of 0.25 molar HCl, we have our chemical reaction there, HCl plus NaOH, single arrow going to water and salt. We know that at the equivalence point, or for neutralization, the millimoles of the acid are equal to the millimoles of the base. You may not have heard that term before, a millimole. We know that we can get moles by multiplying the molarity times the volume in liters. Well, we can get millimoles by taking the molarity and multiplying by the volume in milliliters. And so you're getting thousandths of moles. I find it a little bit easier to work with, and it's one less calculation than having to convert from milliliters to liters, and then potentially back from liters back to milliliters, depending on what your calculation is. So I like working in millimoles. If you're much more comfortable working in moles, then stick with that. They'll both be correct for all the same reasons. So anyways, our millimoles acid equal to millimoles of base. So we have our molarity times our milliliters of our acid here. So that will give us millimoles of acid. And then for our base, we have our molarity of our base times the volume. And so all I need to do is to divide this over here. That will give me my volume of NaOH. And for units, the molarities will cancel and it will give me the volume in milliliters, which again is an advantage to using the milliliters here. But you get 8.03 milliliters of sodium hydroxide should be needed to neutralize that amount of acid. Now, if the stoichiometry of the acid and the base is not 1-to-1, then you need to take that into account as far as the number of millimoles. Now, what I mean when I say that is we've got one HCl and one NaOH. If the acid is polyprotic or if the base is polybasic, that's when you're going to have a stoichiometry different than 1-to-1. Now, if we have a weak base, strong acid, very similar situation to weak acid, strong base. Of course, in this case, since we're starting with a base and adding an acid, the pH is going to start very high. And then as we add the acid, the pH will decrease as we neutralize some of the base and adding acid. At the equivalence point here, the pH is going to be controlled by the conjugate acid, the strength of that conjugate acid from the weak base. So you'll have an acidic pH at the equivalence point. After the equivalence point, the pH is going to be dominated by any additional strong acid that you've added. So once you've neutralized all of the weak base, any additional strong acid that you put in is going to overwhelm the contribution of the conjugate acid in there, and the pH will be pretty much controlled by any additional strong acid that you add in. And so here's an example of what a weak base strong acid titration would look like. So if we have just NH3 to start, notice it decreases very rapidly. We have that very steep slope until we get into the buffer region, and then the slope decreases quite a bit because the pH stops changing. We've now created a buffer solution, and then as we move out of the buffer solution and towards the equivalence point, the pH drops very rapidly. We pass through the equivalence point, which here happens to be at 5.26, and then we just have a slow decrease in pH after that. Then we're just adding more strong acid and really just diluting it at that point. Now, if we want to titrate polyprotic acids, these titrations give multiple equivalence points. So if it's diprotic with 2 H pluses, you'll get 2 equivalence points. If it's triprotic like phosphoric acid, then you should see 3 equivalence points. You get 1 for the first hydrogen. That'll be at a relatively low pH, depending on what the Ka is. The lower the Ka, the lower the equivalence point is going to be as far as the pH. And then each subsequent equivalence point will be at a higher pH as that Ka decreases. What that means is you have to get more and more basic to get that hydrogen off of your polyprotic acid there. Then anytime that we do a titration, we use things that are called indicators. And indicators are themselves weak acids or bases that have chemical properties that cause them to be very highly colored at certain pHs. Some of them turn from one color to another color. Some turn from colorless to a very bright color. We use these indicators in order to tell us what pH range we're in. And so at a given pH, either the acidic or the base form of the indicator will dominate, and that color will be present in the solution. Because they are so highly colored, we just need them in very, very small concentrations because they are themselves weak acids or bases, and if they were present in too high a concentration, they would interfere with our titration. But we can usually have them present in solution at concentrations of 10 to the minus 5 or 10 to the minus 6 molar, and that gives us plenty of color because they are just so highly colored. So what happens with an indicator is as that pH changes, at some point depending on the indicator, the form of that indicator changes, and it changes very rapidly from the acidic form into its basic form. And at that point, a color change will result. Now we have to be careful. We call the forms of the indicator the acidic form and the basic form. That doesn't mean it's an acidic or a basic pH. We have acid to base forms change pH ranges of 2 or as high as like 12. We'll see that here in just a moment. But here's an example of a very common indicator, phenolphthalein. It is a colorless indicator in acidic solutions. And so as we go, here after 20 milliliters, we're still colorless. Here at 40 milliliters, we're still colorless. And right at the equivalence point, it begins to turn very faint pink. And that's when you know that you're essentially done. If you go too far, then it gets even more brightly colored in that higher pH, and you've gone much too far to get a volume reading for your equivalence point. But let's take a look at a chart of some different indicators in here, some pretty neat ones. We have something like crystal violet. Crystal violet goes from a yellow to a rich blue. It passes through a green at a very acidic pH. This is where it loses its hydrogen and goes from its acidic form to its base form. Thymol blue reaches an orange right around a pH 2. You got all kinds of different ones in here. Some of these colors don't show up very well on the screen. They're better in the original graphic. But you can see that we have all these different pH ranges where things turn color. And so if you want to do a titration, you have to know right around the pH where it's going to change color, and then choose your indicator very carefully. If you are just doing a standard strong acid, strong base, very common one is phenolphthalein. Even though it's changing color right around here of about 8.5 to 8.7, because the volume to pH slope is so steep at that point, that will still give you a fairly accurate volume for your equivalence point. Sometimes what people use is methyl orange, which isn't in here, for weak base strong acids like an ammonia titration that changes somewhere around in here. So all kinds of different ones. Bromthymol blue is also a common one for that. Those are a little bit harder to see the change because they're turning from one color to another color. These phthalenes are wonderful because they change from colorless to brightly colored. So they're very easy to use. You just have to make sure that they're going to change in a pH range that suits your particular reaction. All right, well, that finishes out all of our parts of Lecture 4. I hope they all made sense. If not, as always, send me an email, come talk to me in my office, but make sure you get some help to clear up anything that you have questions on. Good luck.